And so we define a linear regression equation as the algebraic description of the linear relationship defined by y hat equals b naught plus b1 x. And then we're going to elaborate on what those variables are. X is the explanatory variable. We covered this last section. Y hat is not just the response variable, but it is the predicted response variable. And what I mean by that is that's what this hat means. In statistics, anytime we put a hat on something, we're saying that's what we're estimating it to be. And I'm going to explain this a little bit going back to proportion talk because I'm hoping this makes sense to you. We said that P is the population proportion and P hat is the sample proportion. That should make a lot of sense with what I just said because the hat means this is what I think that is. So when we say P hat, what we literally mean, if we were to translate this, think about like when you translate, English to Spanish or something, right? Sometimes the translations don't work exactly like you think. It translates to something else, and then we interpret it that way, right? That's what's happening here, right? When you say in Spanish, when you say me amo, whatever, right? You're saying I am called, right? You're not saying my name is, but we translate it in English as my name is, but that's not what you're saying. You're saying I am called this, right? When you say P hat, what you're saying is I am predicting the value of the population proportion to be. And then that should make sense. Oh, well, that would be called the sample proportion, right? When you predict the population proportion, when you think the population proportion is something, that is the sample proportion, right? Because we said that the sample proportion is the point estimate for the population proportion. It's my best guess. The same thing here. When we say y hat, what we're saying is I don't know what y is. Just like in that case, I didn't know what p is. I didn't know what the population proportion was, but I could make a guess at it. I could predict it. And when I did, I put the hat on. I said, oh, the predicted value of the population proportion. That's what we're saying here. I don't know what y is. When I say y hat, I'm saying the predicted value of the response variable. Y is the actual response variable. Y hat is what I'm predicting based off of this line. Okay, what we're talking about here is if you flip back and you see um, a picture of a scatter plot and you draw that line through it, the point is x, y. That's got an actual x value and an actual y value. The line has an x value, but it's not the same value as the y, right? The point on the line is y hat. It's a little bit different than y, which would make some sense, right? It's this idea that when we talk about these regression ideas, what we're saying is I observed an x, y point, y hat's what I would have predicted that point to be based on the accumulation of data. So y hat is that predicted response variable. So a new symbol to add, make sure we understand what we meant, that y is the actual response variable, y hat is the predicted response variable. And as we talked about, the number in the equation by itself is the y-intercept. The number next to the x is the slope. The order does not matter. You can put b1x plus b naught because, again, 5 plus 4 is the same as 4 plus 5. Make sure we understand that idea there. And I have a note here, kind of like we just talked about, all of the points will likely not fall on the line of the regression equation, which means the actual y will often differ from the predicted y. And again, the symbol for the predicted y, I could have said from the y hat. This is something that normally you may not have written down in your notes. This would be in small font. It would just be part of completion. But I'm having you write this down in your notes because I want to make sure you understand this concept here. Y and y hat are two different things. And you need to make sure that you're very clear when you write y or y hat, you know which one you mean and you mean what you say. Okay, as I mentioned last video, this chapter is a lot of know what you can say, what you can't say, know what's an always, maybe, sometimes, right? And the same thing here. Don't carelessly write y or y hat, and there will be points on the exam where you have to choose between should you write y or should you write y hat. Know which one you mean. The actual y will often be different than the predicted y, and that's the idea that the points are going to be what we observe. Think about that golf example where we had club speed and how far the ball went. That y there of was how far the ball really went. But then we would have y hat, which is how far would you predict the ball to go based off how fast the club was swung. Those are maybe two different numbers. That's okay. All the points will have to fall exactly on the line. Okay. we want all the points to fall close to the line. That goes back to what we talked about last video. The closer the points are to the line, the larger the value of the correlation, which is a good thing. Okay, but um, all of the points will often be off by a little bit. The regression line will go through those points. We'll see how close are all the points to the line. That'll be the value of R, and just make sure we understand that the point itself is X comma Y. The line will be X comma Y hat. That leads us to the idea of a residual, because if all the points aren't on the line, we can see how far away they are. And that's called a residual. It's the difference between the observed value and the predicted value, computed as Y minus Y hat. And that residual is what's important in determining what the line is. In this course, we are not going to go through the formula for how to derive the line. This is something that is done in some elementary statistics courses. I don't feel it's a good use of our time, especially in today's era of technology, because you could put all the points into your graphing calculator or into Excel and it will give a line for you. So in the formula for that, it isn't really overly helpful. This is a little bit different than when we talked about standard deviation back in chapter 2. I wanted us to be able to work through that and work through the formula, and we spent some time with that. And the reason why was because the formula got to the idea of what standard deviation was. And standard deviation is a weird concept. But working through that helps you understand what it is, because you're saying, oh, I'm taking how far away is a point from the mean? Okay, I want to add up all those values, but I can't because they'd add up to 0, so I square them, right? So that hopefully hammered home what the point of standard deviation was. That's not the case here with the regression equation. I can give you the formula. It's not going to make any sense to you. It's going to seem very black boxy. So if it's going to be black boxy, I'll just say, hey, just go to Excel, plug it in. It can give you the equation. What I need you to know, okay, here's what I need you to know, is not the formula for how you find the equation, but that the residuals are what leads you to the equation. The residuals, how far away are all the y values from the y hat values, and the line that we're going to come up with is called the least squares regression line. It is the line that minimizes the sum of the squared residuals. And I harken back to standard deviation there. We have to square here just like we did there, actually. And the reason why is because the residuals, some will be positive, some will be negative. Just like with standard deviation, some of the values in standard deviation were larger than the mean, some were smaller than the mean. So when you add up a bunch of positives and negatives, you get 0. Same thing's going to happen here. Some of the points are going to be above the line, some are going to be below the line. So you're going to have some positives and negatives. So again, just like we did before, to fix that, we're going to square all of those residuals. Those are sometimes called errors, by the way. Again, I can error, how far off were you? Again, not that that's a bad thing. We know that we're going to have some error. We're going to be off a little bit. As in statistics, what we're trying to do is quantify the error, quantify how far we're off. So whether we use the term residual or error, it's the same idea. We're going to square those errors, and then we're going to add them all up. And one way to think about this, and this is not what happens, but one way to think about this is take your scatter plot, plop a line in the middle of it, okay, figure out what all your errors are, square them, add them all up, and see what the sum of the squared errors. Plop another line in there. Do the same thing. See what the sum of the squared errors is. Plop another line in there. Do the same thing. See what the sum of the squared errors is. Whatever line you can find that has the smallest sum of the squared errors is going to be the best line. And that's the least squares regression equation. Now, there's a mathematical way to figure this out. We're not going to, again, cover that. It gets into a rabbit hole. But the idea is we want to make sure that we're picking the line that has the smallest possible sum of the squared residuals, because the residuals are the errors. That's how far off we are, and we want a small error. And again, we can't just add up all the errors because we'll have some positive, some negative. So we square all the errors, add those up, and that number being really small, that's going to give us the best possible line. So when you see the line in the examples that were given and the homework problems, you're going to have somewhere you have to go to Excel and plug those in, or a graphing calculator, either one, and get a line. The line that it's finding is it's telling you this is the line that minimizes the sum of the squared errors. Now, When we get that equation, again, it'll look like y hat equals 4.2 plus 0.7x or something like that, right? We'll have a y-intercept, we'll have a slope. It won't be b naught or b1. It will actually be a number. Those have meaning, and I want us to be able to interpret them. How it might feel a little bit rote with regards to writing out the interpretation, but I want to make sure we understand the components to a regression equation. And in this course, we're going to focus on very simple regression equations, but doing this is a very important exercise because if we were to expand this at any rate and make it more complicated, understanding the two basic component pieces is the foundation. So it's only two pieces. There's only a y-intercept and a slope, but I want us to be able to interpret them, what they mean. And here's how we're going to do that. When we see the slope, let's say the slope is 4.5, we're going to say on average, a 1 unit increase in whatever x is produces an increase in whatever the y value is by 4.5. Or let's say the slope is negative 0.3. I'm going to say on average, a 1 unit increase in whatever x is produces a decrease in whatever the y value is by 0.3 units. Okay, notice the positive, negative, I'm going to use as increase, decrease, and then I'm going to put the absolute value of the slope because I wouldn't say an increase of negative 0.3. That sounds weird. I would just say a decrease of 0.3. And we're going to take the context of the problem just like we were used to doing with confidence intervals and hypothesis testing and other things in this course where you plug in the context of the problem. That's what we're going to do here. We're going to say on average, a 1 unit increase in, the father's height produces an increase in the son's height by this much, whatever it may be. Similarly, we can interpret the y-intercept. We need to pause and stop though and say there are situations where the y-intercept exists, but we don't want to interpret it. Okay, so keynote right there, maybe make a note to yourself, put a star by that. You always can interpret the slope. There is never a situation where you build a regression equation and you don't interpret the slope. But there are situations where you don't interpret the y-intercept. And here's how we know if we should do it or not. If it's not a reasonable assumption that x equals 0, or there's no data points neither, we give no interpretation. We just say we cannot interpret. The y-intercept does have a number, but I don't interpret it. Okay, the interpretation is a way for us to take a number in an equation that may seem confusing and just put it in layman's terms. Hey, every time this happens, this other thing increases by this, right? It's just a layman's term type thing on the interpretation, but the number still exists either way. And so for the y-intercept, if x equals 0 is not a reasonable assumption, we say there is a y-intercept. It is this number, but I'm not going to try to interpret it because there is no layman's term I can give you for that. Okay, and we'll see an example shortly where that's the case, where x equals 0 is not reasonable. If we can, then we're going to interpret it like so. When the explanatory variable in x is 0, then y, whatever y happens to be, is expected to be blank. So when x is 0, y is expected to be 4.5 or whatever that may be. Okay, so again, plug in the context of the problem for x and y. And note, I'm using the phrase expected or on average, and you can crisscross those. There's nothing magical about the way I did that. I put on average in the slope and I put expected in the y-intercept. You could flip those and you could say, if you want to turn back to the previous page notes, you could say a 1 unit increase in the explanatory variable is expected to produce a whatever for the slope. And on the y-intercept, you could say on average, when the explanatory variable is 0, the response variable is blank. You don't have to put both. You shouldn't put both. That's kind of overkill, but one or the other needs to be involved there. And they could be used interchangeably. This is the idea that we talked about at the start of this video, that when we talk about regression as a concept, what it means is these are the things that tend to happen, but we don't know that's going to happen. And I think this will really make sense here when we get to the examples. They're coming shortly, so keep your patience on those. I know some of you are wishing they'd already come. But I think that'll make a lot more sense when we get to those examples. If it's a little fuzzy, it's that we're saying this is what tends to happen, but we don't necessarily know if it will, unless we have a deterministic relationship. And a deterministic relationship is a perfect relationship. It's that idea that we talked about with r equals -1 or 1. If all of the points do exactly fall on the line, remember that's what r equals 1 or r equals -1 means. If all of the points fall exactly on that same straight line, you don't actually have to use that phrase because you know exactly what's going to happen. It's deterministic. I can determine what will happen with y based off of x. But most of the time, that's not going to be the case. Most of the time, r will not be 1 or -1, which means I cannot determine what will happen with y based on x. I can guess and be reasonably close, and I have an idea of what will happen, but I cannot predict it exactly. And that's where I want to make sure we understand the distinction between cases where r equals 1 or -1, where we say, I know what's going to happen. I don't need to say on average, or this is what I expect. I know. But in the cases where r is not 1 or -1, and I don't have this, all the points fall exactly on the line, perfect deterministic relationship, I have to say this is the trend, this is what we think will happen, this is what generally happens, but it's not an absolute, okay?